Here's some synthesis practice, mostly taken from the second half of chapter 19. And in this first one, we're trying to take benzene and convert it into this para-di-substituted compound. And if we look at the compound we're trying to make, we have no way of directly attaching this particular tertiary alcohol to the benzene ring, but we could do this by acylating and then doing a Grignard on this to make that. And then in terms of making this compound, we need to alkylate first and then acylate because we need to get the para regiochemistry, and also because once we've acylated, we couldn't alkylate. So going forward, we alkylate pretty straightforward with a tertiary alkyl halide. We acylate. So now we've got our regiochemistry set up. And then we just need to add a second propyl group with propyl magnesium bromide and water. And then that will give us our final product. So here's another benzene compound. So we start with benzene again, and we make a meta-disubstituted compound. And we only have two ways of making alkenes. One is by elimination, which A, is not always reliable, and B, if you look at this, we're adding a carbon to the alkyl chain. So in general, a better choice for an alkene is a Wittig. So if we could get to this point, then we could react this with the methyl Wittig. And so in order to get to this point, we're going to have to acylate, then chlorinate to set up our meta regiochemistry. So going forward, we acylate, we chlorinate, which goes meta, and then we're going to add this kind of silly looking thing, which is the Wittig that you get from methyl iodide. So you take this methyl iodide and add triphenylphosphine and then butyllithium to make the Wittig, and then you add that and get that. Some of you might ask why methyl iodide as opposed to methyl bromide or methyl chloride. And the answer is actually practical more than leaving group ability. Methyl iodide is a liquid at room temperature, and the other methyl halides are gases, and gases are kind of a pain to work with in the lab. You can't just pour it out of a bottle into a beaker. You have to have a gas line, and gas lines are interesting. So here we don't have a benzene compound. We have a secondary alcohol that we need to turn into an alkene. And again, at this point, if you have an alkene, and especially if you're adding carbons, you want to think Wittig. And when we do the Wittig, just as when we do the Grignard, you want to think about which piece of so you look at the carbon-carbon double bond you make, and you want to look at which part came from the carbonyl and which part came from an alkyl halide. And our choices here are to make this piece the carbonyl, which would be an aldehyde, and then have this the alkyl bromide. Problem is that that's a secondary alkyl bromide. So a better choice in green is to make the primary piece into the Wittig and then add the carbonyl. And so starting with this starting material, if we were going to use the red pathway, we would have started by oxidizing the alcohol, which might seem like the more intuitive thing to do, which is why I wrote it the other way, just so we can practice these things that aren't intuitive. So the intuitive thing to do is to oxidize this, and that's exactly what we're going to do. Sorry, I got confused. So we're going to take this compound and we're going to oxidize it. I wrote this in green to match that green, to the ketone, and then we're going to add a Wittig, which came from a primary alkyl halide and checking our carbon chain 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And that makes the Wittig. So again, we choose the green pathway, not the red pathway. Then for number 4, we have a ketone, and we need to do 2 things here. We need to add an oxygen somehow, and we also need to make that carbon-carbon bond. And so the logical way to make the carbon-carbon bond is going to be by using a Grignard. So moving forward, what we're going to do is, if we can get to this ketone, which we can via the Grignard and then an oxidation, and then we can, the Baeyer-Villiger will give us that. So we're going to start with our aldehyde. We're going to add ethyl magnesium bromide to make a secondary alcohol. We then oxidize that secondary alcohol to a ketone, and then we can use MCPBA or another peracid to make the ester. If we were trying to make the ester where the oxygen was on the other side, it would have been a different reaction. We could do it, but we'll learn those reactions in the next chapter. And finally, the last one. So what we're trying to do here is take this compound and convert it into this compound, which, if you don't think too hard, is pretty easy to do. I mean, you might think, well, this is the world's easiest problem, because all we have to do is take this ketone and add methyl lithium or methyl magnesium bromide and add that methyl group. No problem. Ketone, tertiary alcohol. The problem is that the aldehyde is more reactive than the ketone. And so best case scenario, your organometallic compound is going to react with both of these. The reality is you'll probably get more of the reaction you don't want than the reaction you do want. But we can exploit this enhanced reactivity of the aldehyde to protect it selectively. So it turns out that you can selectively protect an aldehyde in the presence of a ketone because the aldehyde is that much more reactive. And so we're going to protect just the aldehyde as the acetal. This is now protected. We can react the ketone with either methyl magnesium bromide or methyl lithium is probably what you might actually use in this particular case, but either one is fine at our pay grade. And that's going to give us this intermediate, and then we're going to add aqueous acid, and the aqueous acid will protonate this oxygen and also hydrolyze off the acetal.